So here's some problems for the practice test for rotation. So there's a sign for the Balsan cookie company with this much mass hanging on a horizontal pole, and you can see that in my little drawing here at this much distance out, 2.7 meters from the store entrance. If anybody was trying to steal this sign, they should know how much torque it exerts. And this one is really straightforward. Here's the torque, the Greek letter tau equals force times lever arm, and there technically it also depends on the angle, but the two are perpendicular to each other, and that gives the maximum torque. So the lever arm is horizontal, and the force, which is the weight of the sign, actually is vertical, pulling down. Hence the two are perpendicular. Okay, so basically all that happens here is plug in the force, which is 18 kilograms, which of course is wrong because it's 180 newtons. So if the mass is 18 kilograms, then the force is 180 newtons times 10, or 9.8. As I said before, you may use either one of those. So times 2.7, and so just plugging in. There we go. Get rid of this one here. So 180 times 2.7, 2 sig fig. 486, 490 newtons. By the way, if I had used 9.8 instead of 10, then this would be the weight, 176.4, a little bit less, times 2.7. And that comes out to, whoa, okay. I meant 2.7. So go back. There we go. Times 2.7. Remember the 486 up there? So 476, one of them rounds to 490, the other one rounds to 480. Either way is fine, just a little bit off from on the end. Newton meters, by the way. Newtons times meters, so Newton meters. There is no abbreviation for that. That's the equivalent, actually, of the foot-pound in the American system for torque. Of course, there would be a conversion factor. By the way, this one here, if anyone was going to steal the sign, there's actually a neat, interesting story that actually 10 years ago it did happen, that someone was stealing this particular sign as a prank, and the police investigated, and I don't think anything came of it. And the company actually, the kidnappers of the sign, they wanted the company to donate this many boxes of cookies to a local children's hospital, that kind of thing. Anyway. All right, I'm going to take a little break here and then go to the next problem. All right, so for this one, a vehicle of this much weight, 14,000 newtons, which is in the neighborhood of 3,000 pounds, so actually not that heavy, is stalled 1/3 of the way across a bridge. Compute the support force that needs to be supplied at the support of the bridge farthest from the vehicle. And the problem is actually really simple once you realize how to do it. So here's the shortcut, which says that at the far end, 1/3 of the weight is being supported. At the close end, 2/3 is being supported, simply because that's where the car is closer. Hence, there has to be more support force. So 1/3 at the far end. So here's the other calculation. So 1/3 times 14,100. I think that divides nicely by 3. It does, 4,700. And on the other side, it's 2/3. So I should have just typed this. It's just as long to do this. 9,400 newtons. So it asks for the far side. So this one here, the 4,700, would be the correct number. And yeah, the other one is 9,400. By the way, they didn't tell us how far the bridge is, but that actually doesn't matter because the distance, the length of the bridge, doesn't actually matter as long as the car is stalled 1/3 across the bridge. Then our calculation is correct. Okay, this was the shortcut, by the way. See, here's the proper way of looking at it. This whole thing has to be in rotational equilibrium. So the vehicle here tries to rotate everything downward, here kind of like in a clockwise direction here, which means there must be a torque that is producing a counterclockwise torque, and it's this one here. It's a support here. If this support wouldn't be here, well, then the whole bridge and the vehicle would rotate actually down, and you would have a catastrophe. So you need, in order to balance this torque here, you need another torque over here, and that's what it says here. The sum of the torques equals 0, and if we measure from the left end, then we have these three torques: the torque on the very left, the torque on the vehicle, and the torque on the very right. And then when I plug these in, force times lever arm, force times lever arm, force times lever arm. And then again, if I measure from the left end, so if this is my 0 point here, then this here would actually have 0 lever arm, hence I put a 0 here. And then here, this is where I put now the vehicle, so it's negative 14,100 newtons times the lever arm of the vehicle, which says 1/3. And then this one here is the support force, the unknown support force, times, and this would be the full length, 1 to the other side, times length. And then notice that as the 0 here is gone in the algebra, each of these terms has the length L of the bridge, and that's why this one divides out, which is exactly what I'm saying right here. So therefore, the support force over here equals this one here, but because that goes to the right-hand side of the algebra, that's why you get a positive there, and therefore it's 1/3 times 14,100, which already I calculated earlier as 4,700 newtons. And if I look at the close end here, well, at the close end, either do 2/3 of the weight as I did earlier, or subtract the 4,700 from the total of 14,100, so that is obviously 9,400. And of course the two forces here from the support force also add up to the total weight in order to support that. So there are two equilibrium conditions. One of them is for torques and the other one is for forces. All right, again, I'm going to take a little break here. All right, so we have the Earth here and we have something orbiting here, which is either the space shuttle or the International Space Station. And this little arrow here, that actually is out of sync there. Both of them are supposed to point really close to the Earth's surface. They're both in low Earth orbit, very close to the Earth's surface. That's why I tried to indicate here. Of course, they're much smaller. So in any case, calculate the acceleration due to gravity for space shuttle territory 411 kilometers above the Earth's surface. And prior to that, it says many people mistakenly believe that the astronauts that orbit the Earth are above gravity, as if gravity miraculously turns off, which is not the case. The reason why they do feel weightless is because they're in permanent free fall. The reason why they don't crash into the Earth is that they also have an incredible amount of speed taking them forward, which is around 17,000 miles per hour in low Earth orbit. And that combined, the velocity that they have in their orbit and the free fall that tries to pull them down, that actually produces the orbit. In any case, we're supposed to figure out what the gravity is just a little bit of the Earth's surface. I mean, 411 kilometers is still 250 miles up, but compared to the Earth's radius, that's actually relatively small. So if we measure 9.8 on the Earth's surface, we ought to measure something less at a higher altitude, but not that much less. Maybe around 9.0, the way my drawing shows here, again, that the Earth's orbit is actually, low Earth orbit is actually pretty close to the surface of the Earth. Okay, there are two ways of doing it. One of them is the proper way, which I posted down here. That's the gravitational law. I will do that second. I will actually start out with the shortcut. So it says in the shortcut, compute the ratio between altitude and Earth's radius. The altitude is given as the 411 kilometers. So I compute that ratio. 411 divided by 6,380, and I have to look up the radius of the Earth. It's not given in the problem. So that gives me 0.0644. I'm just going to write that much down. And because it's a ratio, it doesn't have any units. Okay, I double that. The reasoning here, I will explain it later once I do the other calculation. For now, that's what I do. Ratio 0.0644, then I double it. So 2 times that is 0.1288, which is a percentage of 12.88 or 13%. Okay, that's how much less gravity is. So it's about 13% less, which means it's 87% of the total of the 9.8. Okay, I think you can see that, right? I just subtract the 13% from 100. I can also put it back as a decimal, so I could also write 0.87 right there. So let's see if my calculator shows. I think it does. So 0.87 times 9.8, and I come up with 8.5. So a little bit less what I said earlier. I said 9.0. So it comes out to an rounded 8.5 meters per second squared. I will explain this here in a minute or so. So this is the shortcut. Now here's the proper way. The proper way uses the gravitational law, which is this one here. I guess it's at the bottom of the screen. I'm not sure if I'm able to get that better on here. There we go, maybe here. Yeah, it looks a little better. Okay, so here's the gravitational law. Gravitational constant times the mass of the Earth times the mass of the object that is orbiting it divided by the distance squared or radius squared. And on the other side, I would have the gravitational force, which is the same in this case as the weight of the object, and the weight is mass times gravity, and that's why the mass of the object has already divided out on both sides. And I think I say that here. So that's why you only see one mass in here, which is the mass of the Earth. So here I have written them down. There's the gravitational constant, 6.67 10 to the negative 11. I looked up the mass of the Earth, 5.97 times 10 to the 24 kilograms. And here is the radius of the Earth, 600,380 kilometers, plus the given altitude in the problem of 411 kilometers. And I need to convert that to meters, so I need to multiply 1,000 to get from kilometers to meters. And there is the square, because the gravitational law says it depends on the square of the distance. So here's the calculator. So I'm going to plug in the numbers. There is the gravitational constant. There is the mass of the Earth. Someone could ask, well, how do we determine the mass of the Earth? Actually, very valid question, and it is not easy. We actually use the moon or any kind of orbiting object, and then Kepler's third law, actually, to figure out the mass of an object that is being orbited, in this case, our own planet. Okay, in any case, divide by the denominator, which is parentheses and a second parentheses, 6380, plus the altitude. First parentheses closed, the conversion from kilometers to meters. Second parentheses closed, and don't forget the square. There it is. Enter. And I pretty much come up with the same number as I did earlier, 8.6. I know it said 8.5 earlier, but that's because the shortcut gives a pretty good approximation, and you can see that I think the shortcut was much quicker than this one here. The reason the shortcut works is that it compares the altitude to the radius, and so it says, hey, it's 6% further out, okay? But then because of the square in the gravitational law, something has to happen with this one here, because the force is not 6% smaller, but it's actually yet quite a bit smaller because of the square. So what happens in this approximation here in the shortcut is then instead of squaring something, you actually simply multiply by 2. You double that. So, and it pops out from the algebra if I was to do that, but in any case, I do get 8.5 meters per second squared with the shortcut, or 8.6 meters per second squared with the actual gravitational law. Either one is a valid result. All right, again, a short break for me. All right, and this is the last problem that I want to do. So a projectile is launched at ground level at this angle here above the horizontal and lands downrange. What are the projection angles for the same speed would produce the same downrange distance? And this is really straightforward. Subtract the given angle, in this case 43 degrees, from 90, and you come up with 47 degrees. That's the answer. That's all it is. So here's a little bit of the explanation. This is actually in the textbook. The remarkable thing to note is that the same range is obtained from two different launching angles when their angles add up to 90 degrees. An object thrown into the air at an angle of 60 degrees, for example, has the same range as if it were thrown at the same speed at an angle of 30 degrees. So this is actually the drawing in the book. There we go. And so this is what it just described. Here's the 60-degree angle. It goes to this range. And the 30-degree angle goes to this range. Same one. 75 here and 15 here. In the absence of air resistance, we have to say. Okay, so here I pulled up this applet that you saw there. I guess I have to move this one here so we can actually see it. They have a default here of 80 degrees, but then I would need a very shallow angle of 10 degrees, and for some odd reason I cannot turn it that far down. So the smallest number is actually 25 degrees. I'm going to fire it at 25 degrees, and I'm going to fire it at 65 degrees. So here we go. And unfortunately, that actually goes off the picture. So I'm going to erase that and reset. And I'm going to make it shorter here. So the initial speed, I think the initial speed is actually off the screen. Let me show you what I just did. Oh, it's going to be a challenge. Yeah, because I have to make this smaller here so it fits into the screen. So here's the initial speed. Uh-oh. Seriously, this is a challenge, actually. Trying to fit it in here, going off the screen. I'm doing strange things. So here we go. Actually, maybe since it got smaller, let's see if this works. Oh, just a little bit off the screen. Erase. Do the initial speed smaller. That's good. Let's see what happens. Yep, there we go. Put the target over here. This was 25 degrees. Now I'm going to go to 65 degrees. There we go. Fire again. And in the absence of air resistance, I hit the target at exactly the same point. That pops out from the equations for kinematics for projectile motion, that these two complementary angles fire to the same distance again without air resistance. Okay, that was actually it for these problems from the practice test.